Hello viewers. In this particular session, I will be discussing with respect to the requirements of IR absorption and the theory of molecular vibrations. So first, coming to the requirements of IR absorption. For a molecule to have an IR absorption, or for molecule, or as with other types of energy absorption which we have seen so far, for example the UV visible radiation, a molecule used to absorb the UV visible radiation. Similarly, a molecule which is absorbing an IR radiation, it gets excited to higher energy state when they absorb infrared radiations, similarly as like UV visible radiations. So the absorption of infrared radiation is like other absorption process, and it is also a quantized process. So in order for a molecule where it is showing an absorption of IR radiation, it basically needs to fulfill these two criterias. The first one is the correct wavelength of radiation, and the second requirement it is supposed to fulfill is the change in the electric dipole. So first I would like to discuss with respect to the correct wavelength of radiation. So a molecule absorbs only a selected frequencies of infrared radiation, and in this absorption process those frequencies of infrared radiation which match the natural vibrational frequencies of the bonds in the molecules are, or when the radiation matches the fundamental frequencies of the bonds in the molecule, only then and then the energy absorbs, and this absorption of energy serves in the increase in the amplitude of the vibrational motions of the bonds in the molecule. So when a molecule, I was talking like when a molecule absorbs the radiation, only when the natural frequency of the vibration of some part of the molecule is the same as the frequency of the incident radiation. The meaning of this statement is when a molecule is subjected to an infrared radiation, not all the parts in the molecule will tend to vibrate at a given point, but rather whenever a portion of that molecule or the frequency of that portion of the molecule, if its natural frequency, if it is matching with the incoming incident radiation, which is the infrared radiations, only then and then that particular molecule or the part of the molecule will tend to show the absorption of IR radiations. So for example, the natural frequency of vibration of hydrogen chloride molecule is about 2890 centimeter inverse. It is wave number what I am talking now. Therefore, it is seen that the radiation of frequency or the IR radiation of this particular frequency is absorbed because the natural frequency or natural vibrational frequency of HCl is at 2890, and since it is matching with the incoming radiation at the exact frequency, that is 2090, the absorption takes place, whereas the remaining frequencies, that is from 400 to 4000, if you are creating or if you are inciding like if you are creating those set of IR radiations and making to fall on a molecule, only this particular radiation is absorbed because that is matching with the vibrational frequency of this particular molecule, whereas rest other frequencies, they are not absorbed, they are simply transmitted. So when there is 100% transmission, it means that there is no absorption happening, or if there is some amount of absorption, then it is like the 80% transmission, 50% transmission, the rest is absorbed and the remaining is transmitted. So after absorbing the correct wavelength of radiation, the molecule vibrates at an increased amplitude. As I was talking just now, whenever the frequencies of infrared radiation which matches the natural vibrational frequencies of the molecule in question are absorbed, and the energy absorbed serves to increase the amplitude of the vibrational motions of the bond in a molecule. So in the coming slides, I will show you an animation where you actually understand what is the increase in the amplitude after absorbing the radiation, how the molecule will tend to increase its amplitude, and that how that occurs at the expense of the energy of the infrared radiation which has been absorbed. Coming to the next requirement, which is a very crucial requirement, which is the electric dipole. Electric dipole is a very important thing which a molecule should possess in order to have an absorption of infrared radiation. And we know that an electric dipole deals with the separation of positive and negative charges found in any electromagnetic system. And a simple example I can take here is the system where a pair of electric charges which are oppositely charged and are of equal magnitude and are separated by some typical small distance. I can take that, yeah, here is a molecule which is showing an electric dipole. I have a system which is having a pair of electric charges. For example, this is a hydrogen fluoride molecule which has slight positive and slight negative charges, and there is a set of magnitude or equal magnitude of these charges on these two atoms, and they have opposite charges and they are typically separated by some distance. When such is the case, we call it as an electric dipole, and this electric dipole is found in electromagnetic system. So when I'm talking about a molecule being an electric dipole or possessing electric dipole, in some way that molecule possesses an electromagnetic system in itself. So this molecule, if it is behaving as an electromagnetic system in itself, that electromagnetic system may or will interact with the incoming electromagnetic system, that is nothing but the infrared radiations, which is nothing but the electromagnetic radiation. It is basically the encountering of one electromagnetic system with the incoming electromagnetic system, where the electric vector of both will coincide and tend to vibrate, and this increase in the amplitude of vibration will result into the absorption of IR radiations. So a molecule can absorb the IR radiations when its absorption causes change in its electric dipole. So when a molecule which is having an electric dipole, if that electric dipole molecule, if it is being subjected to incoming electromagnetic radiation, in particular the IR radiation, that causes the change in the electric dipole. So as I was talking, a molecule is said to have an electric dipole when there is a slight positive and a slight negative charge on its component atoms. I have taken an example of hydrogen fluoride, and this hydrogen fluoride has an dipole moment and the bond is quite polar. And whenever there is a dipole moment, the bond, we usually say that the bond is polar in nature. So when a molecule having this electric dipole is kept in the electric field, I mean to say when it is subjected to the incoming electromagnetic radiation, the electric field exerts force on the electric charges in the molecule. So I was talking when this is behaving as an electromagnetic system by itself, and when this electromagnetic system interacts with an incoming electromagnetic system, I mean to say the electromagnetic radiations, the electric vector of this incoming electromagnetic radiation will the electric vector in particular will tend to act on these charges, and that incoming radiation will exert forces on these electric charges, so that these molecules will tend to, or these atoms will tend to move apart, or they either may tend to stretch or they may tend to retract because they are interacting with the electric force field. Opposite charges will experience this force in opposite direction. This will tend to decrease the separation. I mean to say the separation between the hydrogen and fluorine will tend to increase and decrease because they are interacting with the alternating electric force field of the incoming IR radiations, and because this hydrogen and fluorine are slightly charged in nature, they respond to the electric force field, and that's why this electric force field exerts a force on these charges, and these atoms tend to move in opposite direction. Either they may expand or they may retract. So as the electric field of IR radiation is changing its polarity periodically, the spacing between the atoms or the charged atoms or the electric dipoles of the molecule also changes periodically. I mean to say a bond which is possessing an electric dipole, it changes, it is I mean to say, the electric field of an irradiation, when it is changing its polarity periodically, the spacing between the atoms also changes periodically, because the atoms are having opposite charges, and the electric vector responds to these two opposite charges. And the changing electric dipole of the bond can then couple with the sinusoidally changing electromagnetic field of the incoming radiations. So when these charged atoms vibrate, they tend to absorb the IR radiation from the radiation source. If the rate of vibration at charged atoms in the molecule, if it is very fast, or I mean to say, if the rate of vibrations at the charged atoms, if it is very fast, the absorption of the radiation is very intense. If it is slow, or the rate of vibration at the charged molecules, if it is very slow, then the IR spectrum will be having a less intense absorption bands. So depending on the vibrations of these charged atoms, if they are vibrating very fast, then we have very intense absorption bands. If they are vibrating very slow, then we have weak bands. Or if they are vibrating at a medium rate, then we have a medium peaks in the IR absorption spectrum. So I have a representation here. So this is a molecule which is possessing a dipole moment. The reason for showing one molecule bigger and the other molecule smaller is because of distinction. I want to make some distinction between these two atoms. And this diatomic molecule, since there are two atoms, when it vibrates, and since it is electric, it is possessing an electric dipole, it possesses an inherent electric force field, because that is an inherent nature of this electric dipole, since it behaves as an electromagnetic system by itself. And it also possesses an electric force field, or the vibration of these two charges will produce or the oscillation of these covalent bonds will possess an electric force field by themselves. And the greater the dipole moment change through the vibration, if this dipole moment is changing is more and more, then more intense the electromagnetic field it is generating. I mean to say, if it is vibrating very fast, if the motion is very fast, then the more intense electric force field is produced. If the motion is slow, then the less intense electric force field is produced. When I have an electric dipole, or when I have a molecule which is possessing an electric dipole, and when I subject this molecule to an incoming IR beam or incoming electromagnetic radiation, which is an infrared radiation, and since we know that any electromagnetic radiations will have an alternating electric and magnetic force fields, the electric force field in particular, if it interacts with the electric force field of this oscillating bond, then you can see both can merge, and then they can couple. And what we call this as, and once they couple, we call that then IR radiation is absorbed. So when the frequency of infrared radiation, this particular frequency, if it matches this particular frequency, we call this process as the IR absorption process. So the coupling of the wave takes place, and the coupled wave now vibrates with the twice of the amplitude of these individual force fields. So when a wave of infrared light encounters the oscillating electromagnetic field generated by the oscillating dipole of the same frequencies, then the two waves will couple and the IR light is absorbed. That is what I mean to say. So the fundamental frequency of this particular electric of this particular molecule which is possessing an electric dipole, it has a particular fundamental frequency, and if this frequency is matching with the incoming infrared frequency, then the coupling of the radiations will take place, and what we get, or what we end up having, is the coupled wave. And whenever there is a coupling of this two electric force fields, then there is a sort of IR absorption. And whenever there is an absorption, there results a peak in the IR spectrum. So if we have a molecule, not all the functional groups, or not all the bonds in the molecule will have same frequencies or wave numbers of absorption. That is because if I have same bonds in two different molecules, I mean to say that two different molecules having the same kind of bonds, but the bonds may be happening in a two different environments in the two different molecules, though the bond is same, but it is, since it is happening in the two different environment molecules, the value at which these bonds vibrate will be slightly different. So this variation of the absorption of infrared radiation serves as a fingerprint, as we humans have a sort of fingerprints. Any molecule, if you have in a nature any chemical molecule, if I take an IR absorption and I want to compare with the other molecules, no two molecules will be having same IR absorption pattern. I mean to say, as we have a fingerprint, we humans have fingerprints and it is unique for each human being. Similarly, these IR radiation or IR absorption bands for a given molecule, they are unique to that particular given molecule. No two molecule will have a same pattern of absorption until unless they are a sort of enantiomers or anything like that. So this was how an electric dipole and the wavelength of exact frequency was a very much desired parameter in absorption of IR radiations. So we have one more thing which we need to have in our mind. Some symmetric diatomic molecules like oxygen, though they are diatomic, since they are made up of two different similar atoms, I mean to say two atoms, two similar atoms like oxygen, nitrogen, hydrogen and chlorine. Since they are diatomic molecules, they have no charge separation because they have being made with similar atoms. Hence, there is no electric dipole that exists in this particular molecules, and that's why they do not show any IR absorption. That's why we call them as IR inactive. So if I want to measure oxygen, nitrogen and hydrogen or chlorine by infrared spectroscopy, that is practically impossible because they do not possess any electric dipole. So since they do not possess any electric dipole moment in them, we cannot visualize their IR absorption patterns. So however, like carbon dioxide and water, since they are possessing electric dipole, they do absorb IR radiations, and if that is the case, that hinders our absorption, or I mean to say our measurement process. If you are operating an instrument at your lab and you cannot avoid carbon dioxide and moisture in the air, so these become a common interference in our day-to-day IR experiments. So we need to take a blank, and that is only possible when we use a double beam instrument. So these two carbon dioxide and water molecules, they possess electric dipole and they tend to show IR absorptions. And since they have this carbon dioxide and water is present in the atmosphere, wherever we try to take the absorption or the IR absorption, we cannot avoid the interference by these two carbon dioxide and water vapors in the air, and that's why we need to take out a blank reading which will take out any absorption because of these two molecules. One is carbon dioxide, the other one is water. That's why a double beam instrument is very helpful whenever we are dealing with the IR measurements. So I have one more thing here where I need to make a note of. A symmetric bond which has identical or nearly identical groups on each end of this bond. For example, ethylene, if you see, there is a double bond and we have CH2 here and we have CH2 here. If this is the case, I mean to say, if this is a symmetric molecule which is possessing an identical groups on the either side, then it does not possess any electric dipole and hence it does not absorb any infrared radiation. For this purpose, we need to have a particular thing that any molecule that possesses electric dipole, only that molecule can be visualized in IR absorption. This asymmetric molecule can be visualized, and we can measure this bromoethylene in a given system. So with this, now I will discuss about the theory of these molecular vibrations, where we need to understand a very important law called as Hooke's law. So with respect to the theory of these molecular vibrations, At ordinary temperatures, organic molecules are in a constant state of vibrations. We all know that, and each bond has a characteristic stretching and bending frequencies and are and being capable of absorbing light of that particular frequency. So when I take any bond or any molecule, any organic molecule in particular, that organic molecule is made up of so many atoms which are connected by so many different varieties of bonds. And when I talk about these bonds will be having a different vibrational frequencies or fundamental frequencies of vibration, so that one bond will not vibrate at the same frequency as the other. For example, single bond and double bond and triple bond will be having three different vibrational frequencies because they are having a different bond strength by themselves. So we need to consider the bond strength and also the atoms which are joined at either ends of these bonds. So with respect to that particular understanding, Hooke's law is a very important concept where he is talking about the bond strength and the atoms and their masses and their contribution in the absorption of the IR radiations. So we have if we assume two atoms being joined by a bond, and if you think that this bond is just like a spring, then this spring may either stretch or it can be or these two atoms can be stretched across this spring or they can be bent across this spring. So there are two possibilities any bond may possess, either the stretching frequencies or the bending frequencies. So stretching needs more energy, because if you just imagine two balls attached to a spring, if you want to stretch the spring, then we need a lot of energy, then bending needs very little energy. So always the stretching vibrations need a lot of energy when compared to the bending vibrations. So that is the reason the stretching energy of the bond is greater than bending, and two balls joined by a spring is the best example to imagine this. So stretching needs a lot of effort, whereas the bending does not need that much effort. So with that understanding, the stretching absorption of bond appear at higher frequencies because they need more energy in the infrared spectrum than the bending absorption of the same bond. So I mean to say, if you start from 400 wave number and end up till 4000, then the stretching vibrations will appear near to 4000 and the bending vibrations will appear near to 400, because they are very much corresponding to the energy regions, or the stretching needs higher frequency regions and the bending needs a lower frequency region. So it has been found that no two compounds except enantiomers can have similar infrared spectra. As I was talking about this, it can be taken as very much similar to the fingerprints what we humans have, and no two different molecules have a same infrared spectra until unless they are enantiomers. So with respect to this, I was talking about the vibrational frequency. We can correlate this vibrational frequency with the bond strength and the atoms that are joined across these two bonds. I mean to say, a very important concept called as Hooke's law was defined, and the vibrational frequency of a bond connecting two atoms was given by this important law, which correlates frequency with the bond strength and atomic masses. And that Hooke's law is represented as the vibrational frequency, or frequency is equal to frequency is directly proportional to the square root of bond strength divided by mass. So this nu is nothing but the frequency, and this equation was further simplified and they took away this proportionality symbol, so we got equal to symbol with a constant here. So frequency is equal to 1 by 2 pi times k divided by m1 m2 whole divided by m1 plus m2. So k is nothing but the bond strength, and this mass was considered to be as a reduced mass, where we assumed two different atoms like m1 and m2 which were joined across the bond, which we imagined as a spring. So bracket complete to the power half, since we removed this square root symbol. So This is the final equation, which we call it as the Hooke's law, which by using this law we can determine the vibrational frequency of a bond or a system. We can theoretically know at what frequency this bond might vibrate, or what energy any given bond might need in order to respond to an incoming electromagnetic IR electromagnetic radiations. So just to define this K is a constant related to strength of the spring or force constant of a body. So we related that bond to a spring. That's why I call it as strength of the spring. Otherwise, it is nothing but the bond, whether it is a single, double, or a triple bond. M1, M2 are the two masses of two balls which are attached across this particular bond under discussion. So we need to have the masses of these two atoms like M1 and M2, and we need to calculate the reduced mass. I call this whole portion as a reduced mass because I'm not taking only the sum of these bonds, rather it is product divided by the sum of these two particular masses of the atoms. So it becomes the reduced mass. So in order to have the higher frequency, the bond strength should be more and more, or this reduced mass should be less and less. So in order to have this lower frequency values, I need to have the bond strength values, lesser and lesser bond strength values, and more the reduced masses. So that is how we need to we can theoretically calculate the absorption frequencies of any given bond which is being connected by two different atoms. So the vibrational frequency of a bond is expected to increase when the bond strength increases and also when the reduced mass of the system decreases. That's what I just now said. If you increase the numerator, then the frequency will increase. If you decrease the denominator, then the frequency will increase. So this whole thing I call as a reduced mass. If you decrease this denominator, then the frequency will definitely increase. So that is how theoretically we can calculate the vibrational frequency of a bond by using this the bond strength and the reduced mass. So altogether you can put it to understand these two things, or these particular atoms which are being joined by this set of bonds. So thus we can predict that C double bond C and C double bond O. I'm taking a double bond here and a double bond here. We'll have, I'm trying to highlight this bond strength. I'm trying to highlight the bond strength now in this particular example, where I'm comparing the double bonds with the single bonds. Since the double bond is more stronger, the vibrational frequencies, we need to have the higher vibrational frequencies or the more energy in order to bring about the vibrations of this set of molecules when compared to this set of molecules. So the vibrational frequency of C double bond C is more than C single bond C, and the vibrational frequency of C double bond O is more when compared to C single bond O. That is what I meant to say, because the bond strength, I was increasing the bond strength from single bond to double bond. When I increase the bond strength from single bond to double bond, then the vibrational frequency will definitely increase. So in this particular example, what I'm trying to discuss is the kind of atoms where it is CH and OH, and it is CC and CO. So it is a sort of the mass or atomic masses of carbon and hydrogen together, and carbon and carbon, and carbon and oxygen. That is how the vibrational frequencies, if you put together, it is 12 plus 1 and it is 12 plus 12. So it is the higher atomic mass when compared to C single bond H. So if you reduce the mass, then basically the reduced mass, if you reduce this mass, the vibrational frequency will be higher and higher. So when compared to C single bond H and C single bond C, C single bond H will be having higher absorption frequencies when compared to C single bond C. Similarly with OH and C single bond O. So that is how we try to understand or try to correlate the bond strength and the reduced masses by using the Hooke's law. Similarly, the OH stretching absorption will have higher frequency when compared to OD. D is nothing but the deuterium, which is having the atomic mass of 2 when compared to hydrogen, which has 1. So the reduced mass will have the higher frequency. If you increase the mass, then that will be having the lower frequency. This thing you should keep in mind just by looking onto these particular bonds or the atoms which are linked across the similar bonds. Just by looking across these atoms or the bonds, we can predict the vibrational frequencies. So if there is a change in the electronegativity, so for example in this frequencies XH stretching frequencies to fall along the series CH, NH, OH and FH. I mean to say, if you are increasing the electronegativity, then the energy that is needed to bring about the vibrations will go on decreasing. So CH needs higher vibrational frequency when compared to FH, which needs lower vibrational frequency to bring about the vibrations. So I have the energy. I have a set of examples here where I'm trying to show the energy required for excitation increases both by decreasing the atomic masses or by increasing the bond strength, which I have just now discussed. I have a set of examples. So either you decrease the atomic masses or increase the bond strength. So I have an example of OH and C single bond C, where OH is needing, though they are single bonds, uh, the OH is requiring the higher frequency when compared to C single bond C. So now in this particular set of example, I have single bond, double bond and triple bond. Since the bond strength is higher here in this particular case, that is C triple bond C, it needs higher vibrational frequency when compared to double bond and single bond, which has 1650 and 1200 wave numbers. So again, a sort of a comparison of electronegativity and the atomic masses here, and also the carbon, which is linked to various electronegative atoms. As the electronegativity increases, the energy required to bring about this vibration decreases. So this was in general a sort of understanding between the bond strength and the mass of the atoms that are linked across these two bonds. So in the next session, I would be discussing with respect to the kind of modes of vibrations and the fundamental vibrations, wherein which we will understand the kind of vibrations these atoms have in a given set of molecules. So I would like to just flash the slides so that you can recollect the whole thing by yourself. So with this, I would like to conclude this session. Thank you very much for your patience listening.